Welcome to This Explainer. Today, we're going to completely shift your perspective on the physical world. We are zooming way in to discover what a surface actually is. So go ahead and leave your everyday assumptions at the door, because things are about to get weird.
Just look at your smartphone screen or run your hand over your desk. Is anything actually smooth? Well, what feels perfectly flat and seamless to your fingertips is in reality a total microscopic illusion. We're completely blind to this incredibly complex, chaotic terrain that literally dictates how almost everything in our manufactured world functions.
Let's take an everyday object like a car. Beneath the glossy paints and the hidden corrosion protection, there's a whole universe of mechanical interactions happening. You've got valves, seals, piston rings, wheel bearings, brake drums, countless parts just constantly sliding against each other. And the success or failure of this machine? It isn't just about its overall shape or bulk strength. No, it's governed entirely by these hidden, microscopic surface textures.
Part 1: Anatomy of a surface. Peeling back the invisible layers.
Okay, let's dive right into this hidden ecosystem. To navigate it, engineers and scientists rely on a specific field of study called tribology. Now, tribology is basically the science of how surfaces interact when they're in relative motion. It specifically focuses on friction, wear, and lubrication. Think of it as the ultimate rulebook for how materials behave when they touch, rub, and grind against one another, both while they're being manufactured and throughout their entire surface life. When engineers design a part, they don't just sketch out its basic geometry. They have to evaluate what's known as its surface integrity. The absolutely crucial takeaway here is that a surface is a distinct entity. Its properties can be vastly different from the bulk material inside. Surface integrity accounts for the physical, chemical, mechanical, and even metallurgical properties of that outer layer. It dictates everything from a part's resistance to corrosion to whether tiny, microscopic cracks will eventually lead to a catastrophic failure.
This totally shatters the idea of a metal being just one solid, uniform block. If you look at a microscopic cross-section, it reveals a deeply layered terrain that's literally scarred by how it was manufactured and what it's been exposed to.
Let's peel back these layers from the outside in. Right on the very top, you've got contaminants. We're talking dirt, dust, maybe some leftover lubricants from the factory. Beneath that, a microscopic layer of absorbed gas and moisture grabbed right out of the atmosphere. Dig a little deeper and you hit an oxide layer. This is critical because oxide is generally much harder and way more abrasive than the base metal. It's kind of like a crunchy, rough crust. Beneath that crust is a work-hardened layer, which is metal that's been physically deformed and stressed by the force of being cut or machined. And finally, only after digging through all that do we reach the untouched, pure metal substrate. Part 2: Mapping microscopic mountains. How we measure the invisible terrain.
So scientists essentially have to act as microscopic map makers. And to do that, they distinguish between two key features of a surface's texture. First up is roughness, which you can picture as the tiny, jagged, really closely spaced peaks and valleys. Second is waviness, which refers to the broader, more recurrent rolling hills of the surface. You can actually have a surface with low roughness but high waviness, or vice versa. And both of these features dictate exactly how two materials are going to interact. To accurately map all these features, we use instruments called profilometers. Imagine a microscopic record player needle. A profilometer drags a tiny diamond stylus, sometimes just 10 micrometers in diameter, right across the material. As it moves, it records the minute heights and depths of these irregularities. Then, the machines deliberately exaggerate the vertical scale on the resulting graphs. They basically transform microscopic bumps into towering, jagged mountain ranges so engineers can actually study them. Now, because the tools used to cut and shape metal leave behind distinct directional patterns, which, by the way, are often visible to the naked eye, engineers call this directionality lay. They use a very specific set of symbols on their blueprints to dictate exactly how a surface grain should run. Should it be parallel to an edge, perpendicular, angular, maybe even a cross-hatched radial pattern? The direction of this microscopic grain is a huge deal because it fundamentally changes how fluids, like oil, will flow across the surface or how much friction it's going to generate. Part 3: The forces of friction, when microscopic terrains collide. We so often think of friction as just a basic math equation from high school physics, right? But it is deeply, violently physical. When two metal parts slide past each other, their microscopic mountain peaks, which are called asperities, are literally crashing together. The harder surface penetrates the softer one. It plows through it like a tractor tearing through a muddy field, displacing material and physically ripping away tiny slivers of metal. That tangible, destructive resistance, that's what friction actually is.
Because of all this violent plowing and tearing, engineers have to meticulously control surface roughness tolerances based on a part's specific job. Take a bearing ball, for instance. It needs to roll almost completely without friction, so it requires an incredibly smooth finish of just 0.025 micrometers. But jump over to a clutch disc face, which relies entirely on friction to grab and transfer power, and that surface is allowed to be 3.2 micrometers rough. That's over 100 times rougher than the bearing ball. It just goes to show every single part has its own perfect microscopic recipe.
Part 4. The cost of wear. The massive economic impact of friction. $100 billion. That is a staggering number, right? In the United States alone, the constant scraping, tearing, plowing, and oxidizing of these microscopic surfaces results in over $100 billion spent every single year. And that's just to replace worn-out parts. This invisible chaos happening at the surface level is quietly one of the largest economic drains on our modern industrial infrastructure. So it really begs the question, will you ever see a smooth surface the same way again? Honestly, the next time you pick up a perfectly machined piece of metal or just touch something that feels completely flat, take a second. Ask yourself what microscopic mountain ranges, abrasive oxide crusts, and invisible forces of friction and wear are silently playing out right beneath your fingertips. Thanks so much for joining me for this explainer. I really hope it sparked a whole new curiosity for the hidden world around you.